Hi, welcome back. In this video, we're going to explore the solutions to a non-homogeneous system of linear equations. Let's start with a theorem. So this theorem says that any solution to a non-homogeneous linear system can be expressed as a sum of some other solution, a particular solution to the non-homogeneous system, plus a solution to the corresponding homogeneous system, AX equals 0. So if X sub P is a particular solution of the non-homogeneous system, AX equals B, then every solution of that system can be written as X is equal to X sub P plus X sub H, where X sub H is a solution to the homogeneous system. Now let's go through the proof of this theorem, because I think the proof is quite simple and yet a little bit mysterious, and so I want to go through it. Let's start with taking X sub P to be a particular solution. Let's just assume we have a particular solution to the non-homogeneous system, AX equals B. And now let's take X to be just any other solution to the same non-homogeneous system. We want to find a solution to the corresponding homogeneous system such that when we add it to the particular solution, it will be the vector X. Okay? Let's start with A times X minus X sub P. If we multiply X minus X sub P by the matrix A, that's the same as multiplying X by A and multiplying X sub P by A and subtracting. But both of those products are equal to B. So A times X minus X sub P is the 0 vector. Well, that means that X minus X sub P is a solution to the homogeneous system, AX equals 0. So now we can write X as X sub P plus X minus X sub P. And so we've got any solution to the non-homogeneous system, X, and we've expressed it as X sub P plus some solution to the homogeneous system. So that X minus X sub P is just the X sub H that we were looking for. So it's simple, but a little bit mysterious. All right, so let's use this theorem and find a solution to a non-homogeneous system and express it that way. This one says, if possible, solve the following system and write the solution in the form X equals X sub P plus X sub H. Remember, X sub P will be a particular solution to the non-homogeneous system, and X sub H will be a solution to the corresponding homogeneous system. All right, so let's write down the augmented matrix for this non-homogeneous system. So the corresponding coefficient matrix is a 2 by 3. So n is equal to 3. First of all, let's find the rank and nullity of the coefficient matrix. So if we get the reduced row echelon form of the augmented matrix, it looks like this. And the left of that dotted vertical line is the reduced row echelon form of just the coefficient matrix, right? And we can see from looking at it, there's only one linearly independent row. So that means the rank of the coefficient matrix is 1. And since n is 3, we know the nullity has to be 2, because 3 is equal to the rank plus the nullity, and we found the rank was 1. So we know the null space has dimension 2, and that's helpful. So we know in advance we're going to have 2 linearly independent vectors for the basis, for the null space. So now let's take the first row of that reduced row echelon form matrix and write down the equation. It says x plus 2y minus 4z is equal to negative 1. So we can see that we've got two independent variables or two free variables, and so those are going to be s and t. So x is really -1 minus 2s plus 4t. And so we can write the solutions of the non-homogeneous system are all going to look like this. X has to be -1 minus 2s plus 4t is the first component. The second component has to be s, and the third has to be t. And now we can break this up into a linear combination of the vector -1, 0, 0 plus s times -2, 1, 0 plus t times 4, 0, 1, where s and t are just any real numbers. And we can see that x sub p and x sub h are the two vectors. X sub p is -1, 0, 0, and x sub h is a linear combination of the two vectors -2, 1, 0 and 4, 0, 1. All right, let's look at a new theorem. So this theorem says that the system AX equals B is consistent if and only if B is in the column space of A. And the proof of this is quite simple. All you need to do is when you have a matrix equation like this, you write down the m by n matrix A and the n by 1 matrix X and the m by 1 matrix B. And when you do the multiplication on the left, you just get a linear combination of the columns of A. So you get a linear combination of the columns of A on the left, and that's equal to the vector B that's on the right. So that means B's in the column space of A. And we're going to look at an example. So in this example, it says, first determine whether the system has a solution. And if it does, write it in the form x equals x sub p plus x sub h. So we're going to use theorem 4.19 to decide whether or not the system is consistent. So if we write down the augmented matrix for the system, look at the B column on the far right. The column vector is 8, -28, 12. And look at the very first column on the far left, 2, -7, 3. So we can see that the column vector B is just 4 times the column vector A1. So clearly B is in the column space of the coefficient matrix A. So now we can go ahead and find the solution to the non-homogeneous system. So if we do Gauss-Jordan elimination on the augmented matrix, we get this. Notice that we only have 2 non-zero rows, and the first one tells us that x minus 2y is equal to 4, and the second one tells us z has to be 0. So we only have one free variable, y, and so we'll replace it with an s. So x is equal to 4 plus 2s, and z is equal to 0. So now we can write down the solution to the non-homogeneous system. Has to be 4 plus 2s in the first component, the second component has to be s, and the last one has to be 0. And breaking this up, we get the vector 4, 0, 0 plus s times the vector 2, 1, 0. And so this is our particular solution, and the vector 2, 1, 0 is the solution to the homogeneous system. Now we'll end this video with a restatement of our major theorem of the semester. We've already learned that for an n by n matrix, these 6 statements are equivalent. If one of them is true, they're all true. If one of them is false, they're all false. So for example, A is invertible if and only if the determinant of A is non-zero. And the determinant of A is not 0 is equivalent to saying that the non-homogeneous system, AX equals B, has a unique solution for any n by n column matrix B. So now we're going to add 3 more statements that are equivalent to each one of these 6 statements. So the first one that we're going to add is that the rank of the matrix A has to be n. So remember, A is a square matrix. So if it's invertible, or if its determinant is not 0, we know that its rank is n. Or if we know that its rank is n, then we know that the determinant of A is not 0. Also, this means that all the rows are linearly independent and they form a basis for the row space. And the row space has dimension n. That's what the rank means. But it also means that the columns of A are linearly independent. There are n columns of A. So if the rank of A is n, we know the rank of A is not just the dimension of the row space, but it's also the dimension of the column space. So if we find the rank of A is n, then we know the columns form a linearly independent set. So this is the final version of our major theorem of the semester. And so we'll be using this theorem for the rest of this semester. And I'll see you in another video.